water through their heat exchanger, and they got a bunch of silt in here, which they didn't blow out well enough, and a year later they had a sprinkler system, because the silt and against the brass will form under positive corrosion, you'll get pitted. Because you have a different aeration shell because of a different amount of oxygen in the gas stream, remember? Not the gas stream, but the water stream. You won't have corrosion if the fish can't breathe, right? So they had, not potable water, but they had aerated water in the sense that had oxygen in it. And they had this layer of silt here. And within a year, they bought themselves a new $30 million condenser, okay? Now, what the Navy has sort of learned as they've had to go from 30-year ships to 50-year ships is you have to do something more to reduce your maintenance costs. They were running that even if they were still a 30-year ship Navy. But I think somebody probably ran the economics of not just the whole life cycle cost. Acquiring the ship versus maintaining the ship over 30 or 50 years. And certainly when you go to 50 years, they're putting in a lot more expensive material than if you looked at a boomer in the 1960s. I mean, it was a bunch of carbon steel and might have had a high-strength steel shell, but everything inside except in the reactor compartment, which Rickover purchased, right? And he didn't care what he spent, okay? And Congress didn't either, okay? So it was a different era. But now people are putting in cupronickel. I mean, they put in cupronickel back in the 60s in critical seawater systems, but it was only critical seawater systems. Now they'll put in copper, nickel, and Monel, and now titanium more and more. Okay, titanium is becoming very popular because it does have excellent seawater corrosion resistance. You can destroy, it is possible to destroy a titanium condenser. While I'm waiting for this to switch over to my VGA system, I'll tell the story of, this was in the early 2000s, right? Sometime probably within a year of the World Trade Center collapse. Near the world, within a couple of blocks of the World Trade Center collapse, there was a high-rise building that had a titanium heat exchanger, and for whatever reason they had to replace it. But it's so big, you couldn't just truck it out of the building. I mean, they had that way for semis to drive down there, but this thing is bigger than that. I mean, these things can be the size of a 2-story house on a big system, as you guys should know. And so they hired a bunch of guys who probably couldn't speak a lot of English, and they basically had them go in to flame cut the titanium and cut it in parts so they could take it out before they put a new system in. And the problem they had was you can flame cut titanium. It's generates lots of smoke and other things, but nonetheless, you can flame cut it. And these guys came in on a Thursday, and they were cutting it up into pieces. This thing doesn't have a good way to switch from HDMI to VGA. And I didn't have it for my HDMI data. But anyway. So they were flame cutting it, and they noticed on the second day, as this whole area was getting hotter and hotter, they had to cool things down a little bit. And so they would take a hose, a garden hose, and they would spray it on to cool down the heat exchanger that they're flame cutting. And they had noticed that sometimes when they sprayed the water on the titanium, the flames got bigger. Because this is sort of like 3-mile and zirconium tubes. The titanium, if it's hot enough, can react and form titanium oxide and hydrogen gas. Okay, you can start burning your titanium. So titanium is an interesting metal. You really shouldn't be using, they call it purple M, which is a sodium chloride or potassium chloride, some salt, to extinguish it. And so they kept on doing this, and through Friday the flames got bigger when they tried to cool it off, but then they would die down as the hydrogen burns off and the water evaporated. And so the fire department, they finally called in the fire department because this thing's running away on them. They're going to have a meltdown. Okay. And so they finally call in the New York City Fire Department. Fire department comes in, looks at the situation, and the fire chief knew he needed a Purple M truck. But it's out at LaGuardia, okay? There's only one Purple M truck in the whole New York City Fire Department. It may be the only Purple M truck in any fire department in the whole country, okay? There's not a lot of metal fire trucks, okay, that have enough to put out a big fire like this. So they're waiting for the Purple M truck, and the thing is still running away, and they finally have a low order hydrogen explosion. It does $10 or $15 million worth of damage. But anyway, so then the people who were cutting this up sued the City of New York Fire Department for not having put out the fire, which they have been generating for 3 days. Okay.
Did they win?
Huh?
Did they win?
No, I defended the City of New York, and they finally had to admit that they were stupid. Well, they didn't admit they were stupid, but they, you know, we did get them to go away.
So in this, is this the example of hydrogen being destroyed, or?
Are we set up again?
Yeah.
Because I will. Hydrogen being destroyed.
Sorry, titanium being destroyed.
This is the example. I can't remember exactly what it was they had done to the titanium heat exchanger. I think they did have an under deposit type of thing of poor maintenance on the titanium heat exchanger. You can, well, to quantify the thermo for the corrosion, it takes 0.8 of a volt to do cathodic protection, or some people say 0.85, etc. 0.83, who cares? Volts to protect cathodic protection of steel. It takes 1.1 volt to break down water. Remember in high school chemistry class, you made hydrogen and oxygen. Titanium requires 5 volts. Okay, this is just the Gibbs free energy converted to voltage. Okay, and so titanium is. I mean, there's not very many things that are better than titanium. Okay, and we'll get to those actually in a few slides here. Things like tantalum. By the way, do we have until 9:30 today?
Yeah, but we gotta walk.
We gotta walk over, so we have to 9:20. Okay, so I mean, I want to start getting things in. By the way, also on Monday, we've got Brian, Tom Kane, and Austin Jolly. You guys, all 3 of you here. You know it. It's still okay for it? Okay, fine. And we're only going to do, we said Monday, Tuesday, and Thursday next week, right? For class. So if I'm going to get through my little 10 points here in this PowerPoint and declare victory and let you guys go start watching your welding things, I got to start doing it. So we'll take a little bit of time. What was I just talking about before that? Okay.
The 5 volts for.
Oh, the 5 volts. So this is just the Gibbs free energy, and there's not very many things. So calcium maybe would be higher, but we don't think calcium's not a good structural material. So titanium is somewhat unique. Tantalum's better, but not much better. Still running like 5.3 volts or something. So you just have a hard time generating enough voltage to destroy titanium, the titanium oxide and things. You can do it if you get some clever chemistry and screw-ups. I had a problem once in the 1980s. I used to consult for a division of Johnson & Johnson, made medical instruments, and they were doing electrical cauterization of wounds, okay? So they go in this little forceps that had some titanium tips, and they come in with like 100 volts DC. And they just take that blood vessel and they just sort of fuse it with a little electricity, okay, DC electricity, and stop the blood flow. So it's sort of, fusing together the blood vessel, okay. But they were finding pitting on the positive electrode of the DC circuit. And I said, well, what do you expect? And they said, well, we need a material that won't do this. I said, at 100 volts, okay. There is no way, there's no material in the world. I mean, this is the most stable oxides are only 5 or 6 volts on an electrochemical equivalent, okay? And they were using 100 volts. 100 volts DC will destroy any element, any element in the periodic table, and by a large fraction. And so he said, well, can't you come up with something? I said, no. I mean, there's a fundamental thermodynamic limitation there. Okay, so not all problems are solvable. Just replace the tips. Hey, you can sell more of them, you know? Anyway. Okay, any questions? I didn't have other things. I did want to start
Uranium
going.
doesn't break down.
Pardon me?
I know we were joking, uranium doesn't break down.
Okay. Anyway, when it breaks down very quickly. In fact, I did bring, just for, it's nice to have some touchy feelings. This is a piece of crystal bar zirconium. And they make titanium. They used to make, they make titanium by less expensive ways now, but back when they first started making large quantities of titanium, they basically would make it the same way, and you basically take a wire of titanium or a wire of zirconium, and you make a light bulb out of it in a vacuum chamber, and you introduce zirconium chloride or titanium chloride gas, which like 300 or 400 degrees is a gas. It comes in, it sees the hot wire, it decomposes, gives you chlorine, which you use to rechlorinate some more zirconium oxide and stuff, and you end up forming crystals. It's a vapor deposition process by decomposing the zirconium chloride into zirconium crystals, and you get crystals because you have a big entropy change when you go from the vapor phase to the solid. And that gives you crystals. We won't get into the metallurgy of that, but then you take that, and basically you have to keep that hot. So you can only get so big. I mean, they're putting thousands of amps through that thing to keep it hot, because you just use the electrical resistance heating. You start with a little wire, and you keep growing it bigger and bigger, and you up your current until you can't up your current anymore, and you take it apart. And then you eventually work it down into a zircaloy tube, which is actually an alloy, but it's like 94% zirconium with some tin and some other stuff in it. And that's what they use to clad your fuel in a nuclear reactor. And the reason you use it is because zirconium has a very low nuclear cross-section. Some of you guys are nukes. Boron has a high nuclear cross-section. It absorbs neutrons. Zirconium doesn't absorb neutrons, but that has to be really good zirconium with very low hafnium, because if you look at the periodic table, hafnium is right below zirconium, and when you find it in nature, there's always some zirconium, there's hafnium impurities. Hafnium has a high neutron absorption cross-section. And zirconium is sort of a perfect material. It doesn't melt until like 2200 C or something. Just as corrosion resistant, if not more corrosion resistant than titanium. Okay? But kind of pricey. About $100 a foot for that tube. Okay? So a lot of technology goes into it. The major use of zirconium other than nuclear reactors that I know of in the metallic state is to make acetic acid. Turns out acetic acid, the world's largest use of inorganic acid is sulfuric acid. Of organic acids, the largest use is acetic acid. You make acetate films and all kinds of polymers and stuff out of acetic acid. You can also make cheap vinegar. Okay, but anyway, you can use a nickel-based alloy of chromium and cobalt and molybdenum, which is very expensive. It's a Hastelloy alloy. Or you could use zirconium. And the Hastelloy is kind of like a Navy ship that lasts for 30 years. The zirconium lasts the life of the vessel, okay, which is longer than we all want to count. So there's an interesting story that I had to testify in International Arbitration Association in Stockholm, Sweden, where the Chinese government, I don't know if I'll never get through my lecture. I was working for the Chinese on this one.
What?
You're right.
You're right.
But the British Petroleum Chemicals, BP Chemicals, was the leader in acetic acid production. They had a refinery they bought from somebody else in Texas City, Texas, and they sold the Chinese government. Well, they wanted to partner with the Chinese to make acetic acid in China, since it's a major industrial chemical. And the Chinese, of course, say, no way, we don't partner with anybody. And so they said, the Chinese said, we would like to buy your best available technology so that we can make our own. So BP said, okay, we'll sell you, this is in 1993 or 94. They sold the best available technology in Texas City, that they had in Texas City, Texas, which was actually 1980 technology. And that's what they were using in 1994 in Texas City, Texas. This is 1980 technology with the Hastelloy alloy. And, you know, the Chinese government paid hundreds of millions of dollars for this. Actually, it's a Chinese firm, but it's really state-owned. And they, the Chinese were delighted, and it used a rhodium catalyst, okay? This is one of the major uses of rhodium, which is like a platinum group metal. And when you make acetic acid, as one guy says, it's not really, you're not really making acetic acid, you're running a rhodium recovery plant, because you can't afford to sell the rhodium with, as an impurity in your acetic acid. You got to recover it all, or you lose your shirt. So the Chinese built a whole plant. They had a room full of drawings. I had to fly over one Columbus Day weekend to Shanghai, because it was the only time I could do it, because the Chinese had signed an agreement, they're worse than you guys, you know, that they would not make any copies of this, and they had 2 copies, and I had to fly to Shanghai to look at all these documents, okay, because they couldn't make a copy to ship to me. Anyway, so they were trying to say that the Chinese had stolen the fabrication technology, and because they built another, the Chinese had built another plant, a second plant after they built the first one with the BP technology. When the Chinese learned in 1996 that BP had a new iridium catalyst, which is another platinum group metal, they said, we want to license that technology, and BP said, no, not unless you'll partner with us. We sold you 15-year-old technology, and you can use the 15-year-old technology, and we'll use the brand new technology. And obviously, BP knew when they signed the agreement in '94, they were working on the other thing. They knew that they didn't mind selling the old technology because they had a new, better one coming out. So the Chinese felt miffed, and they decided, well, they were going to show the British and teach them a lesson. So the first thing they did is they went out and designed their own new rhodium catalyst, which was more efficient than the iridium catalyst. Okay, so it was a more efficient process. And they taught themselves how to build a zirconium reactor. Now this reactor is about the size of this room, and it's made out of zirconium, and I told you about how difficult it is to weld titanium. Well, zirconium's just as bad, okay? And I saw the plant in Shanghai. It was like right out of the 1920s. But they were welding zirconium. And they had taught themselves. Well, they hadn't really taught themselves. There are companies, you go down to Texas City, Texas, they'll run a zirconium welding seminar once a year, okay? And teach anybody who wants to pay the fee to come in and learn how to weld zirconium. And so the Chinese came and took the class, publicly available, okay? They took the class, they went back to China, and they had guys sitting there, you know, a million little Chinese sitting there, making these little welds, you know. No one could ever do this efficiently except if you had Chinese labor, right? And they made it work. And so I went and testified in Stockholm that they didn't steal anything from the British, they developed them themselves, and they showed the British. It turns out, I was told afterwards, that the premier of China was waiting to hear of the results of that arbitration, because at the time, this had become a big deal about Chinese stealing, you know, foreign technology, and they wanted to show they didn't steal it. And in this case, they didn't steal it. They actually took 1920s facilities and made, you know, 2010 type of product. So never underestimate their ability, particularly if they feel they've been cheated. Okay? They wanted to stick it to the British. who had cheated them out of a few $100 million. And it was a state-owned company, and I mean, it went all the way to the top of the government. And this was it's a matter of principle. Okay? So, take that story for what it's worth. I don't know what it has to do with corrosion other than zirconium.
What you're saying is we can teach ourselves as well.
Yeah, we can teach yourself. You can film it.
Well, I can tell you some other stories, like most of the solar cells that are going up on roofs around here, technology to grow that was done right up here in southern New Hampshire. And they sold $30 million worth of units to the Chinese. And it's now coming back as solar cells to us, right? But I can bring in some of the pieces of stuff. And that company is now bankrupt because they wiped out, by selling all the technology to make the silicon solar cells, they essentially went to the Chinese, who undercut all the American companies, so the solar cell businesses in the United States all went under, they went under. So, you know, just sell it to the foreigners. Okay, so we've been through the first 2 or 3 of these. Free oxygen, you know, Jason learned that fish you gotta starve the fish of oxygen if you're gonna prevent corrosion. And you guys already know all the things the Navy does on shutdown of a reactor to keep the oxygen out until they start it up again. And even on commercial reactors, they boil the water, literally, to get the oxygen out before they put it back into the reactor system. Okay? It's all on the startup. It's just like starting a car. All the wear on that car is on that first couple of minutes of startup, particularly in cold weather, where the lube oil is not all protecting it. Once it gets running, okay, like police cars, they never turn them off, and those things can go for hundreds of thousands of miles because the lube system works great. There's not any wear when it's operating at proper temperature. It's all the cold start condition. Same thing with the reactor and all the corrosion problems. They pretty much all occur primarily on the startup. Moisture provides the pathway for electrical charge transfer in aqueous systems. And that can be good or bad. But it is the pathway. A few years ago, the town of Belmont that I live in decided to put in 2 new oil storage tanks in 2 of the elementary schools. The fire chief said, wow, I want to be high tech. I want to put in a cathodic protection system on these oil tanks. I don't want to have any oil leaks. And so about 6 or 7 years later, one of the elementary school, well, one of the high school students noticed on the pond in front of the high school, which is downhill from one of the elementary schools that had this new tank, a little sheen of Newton's rings on the water. It's okay, it's only rats and geese that use that pond, okay, but it was oil slick, and it came from, they tracked it back to the oil tank on the top. And what they had done, because I had to come in and help them figure out, they had put their oil tank in the ground. They put their cathodic protection system on it, okay, so it was positively charged, or, negatively charged, okay, you don't want it to be the anode. And then they put some asphalt on top for a parking lot. And this cathodic protection system relies on damp soil to complete the electrical circuit. So they cut out the circuit for the cathodic protection system. And then they basically, this is number 6 fuel oil, and so they have to keep it hot, and so they recirculate it all the way through the tank all the time. And so they ended up essentially corroding away the piping and getting an oil leak in this, you know, double wall tank construction, cathodic and protected, except the cathodic protection didn't work. The other elementary school where my kids go, they dug it up and we looked at it and didn't put a parking lot on top of it, so the soil was damp. It rains in New England, and so they had the cathodic protection worked. Okay, so you have to have moisture in that case to complete the cathodic protection circuit, but in other cases, moisture is the thing that creates the electrochemical potential that causes pitting and other localized corrosion and stuff. We actually use lack of moisture to store old aircraft. Anybody ever seen the pictures in Arizona of the Air Force Base where they have all the old B-52s? And they take the wings off periodically, every couple of weeks. They did this back for the SALT treaty. They would disassemble the wings, and the Soviets could take satellite pictures and see exactly how many B-52s we had decommissioned. Okay, they store them, and they store 757s, 747s after they have about 100,000 hours of life. They just go park them in Arizona for spare parts. Why Arizona? Because it doesn't usually get wet. But anybody from Arizona? When it gets wet, it really gets wet. Okay, they'll have a couple of inches of rain over 2 or 3 days when the storms come through. And then it's really sort of interesting. If you're there 2 weeks later, the desert in bloom with all these flowers and other plants that all pop up, within 2 weeks. So it's kind of pretty. I had a big corrosion problem in a building there once. They were building it was a 1 million square foot warehouse near Phoenix. And it was under construction, and one of these storms came through for a couple of days. And they had put the first level of the roof in and some of the insulation, and the insulation got soaked. So what do? They just put the top layer of plywood on top with their moisture barriers, and they created a little greenhouse in there, a little sauna, so that when the 110 degree days came by during the day, between the moisture barriers in the roof with all that wet insulation, they would heat up in the day, and at night they would cool down. So every night and day they had a little sauna, and that galvanized steel corroded at about 5 times the rate that you would have in the worst possible atmospheric conditions. And their roof was destroyed within a year because they just covered over the wet roof. Okay, they don't. The contractors there weren't used to dealing with wet construction materials. Okay. Anyway, so there's,
So that's just poor planning.
It is poor planning, but hey, I don't know if I put my college on that one, but I can probably pay for a vacation or something, a family vacation. Okay, so moisture provides the electrical pathway. The oxygen doesn't break down unless you have 1.1 volts, and we don't usually have 1.1 volts. Something else is usually corroding in the system at 0.8 volts or something less. And we'll see that when we get to the Galvanic Series. If you look at the Galvanic Series, there's only a few things that go above 1.1 volts, like carbon and zinc. Okay, which actually, you were talking about salvaging. Okay, that's another story. Port Quantum, the Navy's got or they used to have a base at Port Quanumi in California, and this is an underwater systems lab or something. Anyway, whatever it is, they have a lot of divers at Port Quanumi, and so this was 30 or 40 years ago. These guys are not usually developing new materials for the Navy, but they came up with a magnesium carbon composite. Okay, took magnesium metal and they took carbon powder and they mixed them together and made a composite. And it was a super corroding material. Okay, if you look at the Galvanic Series, I mean, you got like 1.4 volts here. And if you were to stick this in salt water, which has good electrical conductivity, you will decompose the water just like your high school chemistry class by just sitting there. You got 1.4 volts, okay? And so they had 2 uses for this. One is it generated enough heat that a diver could strap one of these things on his belt, and if it was in cold water, he could just take his knife and break the plastic bag, and it would generate heat. Okay? Generate a lot of heat. You got to make sure you don't burn yourself against it. The other thing is they were looking at it, I don't know if they ever used it, as a way to generate the gas for salvage. You have it in a plastic bag, the diver takes it down, puts his cables on whatever you want to lift to the surface. Instead of putting compressed air in the bag, just break this stuff, let it generate its own hydrogen bubble. It's just you got to catch it and grab it with the crane before the hydrogen goes boom at the surface, right? But anyway, they could generate gas underwater, out of water, right? Anyway, so it was a super corroding material. So sometimes corrosion can play other benefits for you. Localized corrosion, we'll go through this next week, You've got crevice corrosion, pitting, intergranular corrosion, exfoliation, which is something that occurs in aluminum alloys, certain aluminum alloys that haven't been heat treated properly. All these are localized attack where you're breaking down this protective passive film of usually oxides on the surface. In the case of exfoliation, you're breaking down the aluminum oxide. All these are just small galvanic cells. Velocity phenomena, cavitation, erosion, phoretic, we basically wear away that surface oxide and expose the metal to further attack. There's something called de-alloying or selective leaching, most commonly seen in brass alloys. There's been some billion-dollar lawsuits out in Las Vegas on this, in homes where they use brass plumbing fittings. Even though the code said in Las Vegas water, which is not the best potable water in the world, okay, it's Colorado River water that's been used several times, and it's kind of salty. The brass, they said, you're not allowed to use this plumber's brass for the big gate valves. Well, you can't use it for the big gate valves supplying water to the homeowners, but that doesn't mean that contractors couldn't put it in as the plumbing in the homeowner's house. And so they ended up with sprinkler systems in their homes and plumbing systems, and one case settled for $250 million, and most of the others went away when I told them they were full of shit. But that's another story. Stress corrosion cracking, we can talk about that. We've run in later, we're running out of time. Corrosion fatigue and erosion fatigue are things where I have some mechanical stress combined with a corrosive phenomena, and you end up getting a synergistic effect. Just like I talked about the creep fatigue interaction, how you can have creep in titanium, you can have fatigue in titanium, but you put the stress and the cyclical loading together, and things can go 10 times as fast. Similar types of things with corrosion fatigue and erosion fatigue. We're just combining stressors, two stressors with the corrosion stress. And then there's lots of things we can talk about hydrogen attack. But that's enough for today. Go up to your other class unless you have a question. Okay, so